Our first week of the semester, we were talking about background stuff. So that was mainly things from the first half of the book. So we're now moving into chapter 17, which is the second half of the book, which is really where this class really is supposed to be, is the stars and galaxy class. So what we want to do is talk about properties of stars. And there's several things. You look up at stars, you notice they're not all alike. One of the most obvious things you notice about stars is that different stars have different brightnesses. Turns out they also have different colors, and we'll talk about that later too. So we want to understand about the stars, the brightnesses, and the colors. And so we want to understand that. We want to understand the distances of the stars, and we also want to understand something about maybe the temperature of a star, the size of a star, how big is it, how much does it weigh, and what's it made out of. So the first step, however, is measuring brightness of stars. One of the first records we have of anyone computing or measuring or recording the brightness of a star is Hipparchus of Nicaea. And this was in about 150 or so BC. And so he was measuring the properties of stars and making catalogs of stars and recorded how bright they were. And he did this in a particular fashion that we now call magnitudes. What Hipparchus did was he grouped stars into basically several categories that we called magnitudes. And it's category 1, 2, 3, 4, 5, and 6, where 1 was the brightest that he could see and 6 was the dimmest. Now, actually, he did 5, and then later astronomers added 6 as the absolute dimmest. And so that means that he grouped them in order of what he thought was important. So the most important, he thought, were the bright stars. So magnitude 1 is brighter than magnitude 2, which is brighter than magnitude 3. This is really a confusing thing to students today, because I say, what's brighter, a magnitude 2 star or a magnitude 4 star? And you think the bigger number is brighter, but no. The smaller number is brighter, so that's brighter, and then dimmer is going to be bigger number. Now, later astronomers extended this because they realized that not all stars are equally bright, and so you have fractional stars in between. So you have magnitude like 3 1/4, 3 1/2, 4 1/4, and so forth. And then some first magnitude stars are brighter than others, so they added magnitude 0, added magnitude -1, and the brightest star in the sky, Sirius, is roughly magnitude -2. With binoculars, you can see even dimmer stars, magnitude 7, 8, and 9, and so forth. So the scale keeps going in either direction. This graphic from your book shows the brightnesses, the magnitudes. The sun is roughly magnitude -27. Your book refers to the Hubble telescope as magnitude 30. It's actually gotten dimmer than that by staring at one particular spot in the sky for like 2 weeks straight, and you get almost magnitude 39. Of consequence to you is this right here. Magnitude 6 is the dimmest you can see. So you can see, given really dark skies and good eyes, you can see anything brighter than about magnitude 6. Now, there are some indications that some people with really good eyes can see a little bit dimmer than that, and other people cannot see quite that dim. But that's roughly the naked eye limit, is magnitude 6. Anything dimmer than that requires typically binoculars or a telescope to see. So, the symbol for magnitude, lowercase m here, okay, in this table. So now the question is, what's the brightest star on that list? Okay, now normally in class, I'd have, an exercise, we'd go through, what's the brightest star on the list? What's the dimmest star on the list? And so forth. So the brightest star on the list would be the one with the smallest magnitude number. And that would be this, Alpha Carini. Now remember, last week we talked about Bayer designations. The Greek letter alpha, CAR, is the official abbreviation for the constellation Carina. And so this is the star Alpha Carini. So that negative number makes that the brightest magnitude star. So what's the dimmest star on the list? Well, the dimmest star on the list is the biggest number. So that's right up here. That's going to be the star Wolf 358. Okay. And so that's the brightest and that's the dimmest. Okay. So what's the dimmest one that you can see? Well, typically magnitude 6 is considered the dimmest. So this is almost magnitude 7 right there. So that's too dim. So the dimmest you can see is right there, 44 Andromedae. Okay. And so so we have 44 Andromedae, and that's the dimmest you can see at magnitude 5.7. The dimmest on the list is Wolf 358, magnitude 11.67, and the brightest was Alpha Carini, and that is magnitude negative 0.67. So the next question is, well, how do you figure out how many times brighter? Because we can find out how many magnitudes brighter. Okay. So, for example, for the first two stars right here, we have Fomalhaut and we have Wolf 358, and they are a difference of 10.1 difference in magnitudes. Okay, so we know the 10.1 difference in magnitudes. What about these two stars? Psi Ursa Majoris, okay, and let's say the star Zosma. So what about those two stars? So they're a difference of 0.81 magnitudes. But really, how much is that really actual brightness? Well, one of the things we discover is that if you start looking at this group of stars here that he had from 1 to 6, the way your eye works, that's a difference of 100 times brightness. So a difference of 5 magnitudes is 100 times difference in brightness. Okay. So 5 magnitudes is 100 times in brightness. So if that's the case, imagine that we have these stars up here, okay, and we have star A, star B, star C, okay, and star A is magnitude 2, and star B is magnitude 7, and star C is magnitude 12. And I want to know what's the difference in brightness between A and B. So between A and B, it's 100 times difference. Which one's brighter? Smaller magnitude is brighter, so star A is 100 times brighter than star B. So what about between B and C? That's also 100 times because it's 5 magnitudes. So 5 magnitudes is a difference of 100 times. So star B is 100 times brighter than star C. So now the question is, what about star A and C? So what about stars A and C? What's the difference in brightness? Now, think about it. Students will often say it's 200. Well, think about it. If this is 100 times that, but this one is 100 times that, what's 100 times 100? Okay, let's think, let's think smaller. So let's say that one thing is 3 times the size of something else, and the something else is 3 times the size of the thing, some other thing. So, or let's take a pizza. Okay, so we have a pizza, small pizza, divided it into 4 parts, and then we have 4 pizzas. Okay, and math is always easier when you think about food. Okay, so this slice of pizza is 1/4 of that, right? So we would say the pizza is 4 times bigger than that. Okay, so here, the entire group of pizzas is 4 times bigger than the one pizza. So how many times brighter, bigger is the entire, the entire table full of pizzas than the one slice? Well, it's not 4 plus 4. It's not 8 times bigger. It's 4 times 4, 16 times more. So the same thing holds here. If star A is 100 times brighter than star B, and star B is 100 times brighter than star C, this is 100 times 100 times. So that means it is 10,000 times brighter. Okay, so let that sink in. A difference of 10 magnitudes, 5 magnitudes is 100 times brighter. 10 magnitudes is not 100 plus 100, it's 100 times 100. And so that would be 10,000 times brighter. So let's now consider, remember I said that the sun is almost magnitude minus 27. Sirius is almost magnitude minus 2. So how many times brighter is the sun than the star Sirius? So this is a difference of 25 mags. 25 magnitude difference. So 25 magnitudes is 5 groups of 5. Each group of 5 is 100. So what is 5 groups? Well, it's not 5, it's not 100 plus 100 plus 100 plus 100 plus 100. It's 100 times 100 times 100 times 100. So in other words, it's 100 to the 5th power. So what is that? So what is 100 to the 5th power? Okay. Well, that is going to be 10 to the 10th power. So in other words, that's going to be 10 billion times brighter. Okay, that's why you go out and look at the sun and it hurts your eye. You go look at Sirius and say, oh, that's bright. The sun's not just a few times brighter, it is 10 to the 10 times brighter, vastly brighter. And so that's because 25 magnitudes is 5 groups of 5, and each group of 5 is 100. So it's not 5 times 100, it's 100 to the 5th power. So we could then say the ratio of brightnesses. So what about 1 magnitude? We know that 5 magnitudes is 100 times different. So what's 1 magnitude? Well, again, it's not going to be 20. It's not divide. It's going to be 1 magnitude, whatever it is, to the 5th power. So whatever it is to the 5th power gives you 100. So that means 1 magnitude is going to be the 5th root of 100. Well, that turns out to be 2.512. So that means if you have 2 stars, star A and star B, and their difference of 3 magnitudes, so let's say this is star magnitude 1, that one's magnitude 4, then it'd be 2.512 to the 3rd power. So you just enter that into the calculator, 2.512, and raise that to the 3rd power, and that's going to be about 16 times brighter. So anytime you have stars and you look at that table of data and it says you have a star of 1 magnitude, a star of another magnitude, then the difference in brightness is going to be 2.512 raised to the difference in magnitudes. So the L1 over L2, that's the ratio of the brightnesses. You don't need to know what those brightnesses are. You just know the ratio of them. The difference between them is 2.512 raised to the difference in magnitudes. You always take big number minus small number. Students always want to know which one do you subtract from which. Well, the big number, because the exponent has to always be positive. So it'll be whatever is the big number minus whatever is the small number.